So now we're on to question 5. The previous assignment actually had something kind of similar to the isotherms, right? Different temperatures, you had different isotherms of a gas. So you kind of did something very similar to that in your first assignment. But now we're introducing the concept of adiabats. There's a difference between adiabats and isotherms. One of the things that we are learning is one of the things that a lot of books will show you is the two-dimensional projection onto the P versus V. So thinking bubble, what a lot of books will show you is this, P versus V. And they'll say isotherms, right? Remember how we did this in assignment 1, and they would label, let's just say this was 100 Kelvin, this was 200 Kelvin, and this is 300 Kelvin. They don't want to show you the extra temperature axis. So what they did, and I think I talked about this, what if you were to graph this one, 100 Kelvin? So let's say this is 100 Kelvin. You would draw one graph. Then at a higher temperature coming out of the page at 200, you draw the next one. So what this represents over here is kind of like this surface, right, on a three-dimensional graph if we could graph it nicely. This is simply the temperature axis coming right out at you. Shine a light down on these different temperatures. These are the 3 lines you get. What they're going to do now is, these are isotherms. Adiabats. In adiabatic processes, P, V, and T are changing all the time. Okay? So what you're going to see is, if you project an adiabat on here, they're steeper. So adiabats, the projection of an adiabatic path on this three-dimensional surface onto the PV, see how they look steeper? They cut across isotherms like this. But the reality is, if you were to, in an adiabatic process, you did thousands of measurements along the PV and T, and let's just say you get this sort of surface. Okay? Well, if you started out at point A and you went from one P and V to a new P and V and new temperature, it could be out here. So you see how whatever this surface looks like, this goes from initial, so let's just say P1, V1, and T1, and then you end up over here at P2, V2, and T2. This path on the surface of an adiabatic process, this becomes the specified path you took from here to here. I could shine a light of it onto the PV, right? And this is what a lot of textbooks show you. But this is sort of the full story of what we're talking about. So your exercise is to say, okay, we are going to graph 2 relationships. So I'm just going to show how I formed it here for you. You have to basically mathematically graph the isotherms, the 2 isotherms, and the 2 adiabats. So quite frankly, imagine if somebody said in your question, you have an isotherm at 273, and it gives you are going to populate as many as you need. This chart, I'm suggesting values for volumes you can start with, right? And the P's, for instance, at 273, you can populate your chart here so you get the nice shape visibly of that isotherm. You put in all these points needed to get the second one, and do the same thing for the adiabats. So let's start with isotherms. At constant temperature, we already know the Charles law is here. So what you do is you say the second pressure, which I'm going to calculate mathematically, is going to essentially equal what the P1 and V1 was, right? So let's just say you started off for the hell of it at 1 liter, and the corresponding pressure that would match it for an ideal gas, right? You would get this K. So you would end up saying, I want to graph P2, right, versus this constant 1 over V. So y equals some constant K that you'll calculate. So what I've done here is I said, okay, at 273, let's pretend you have 1 mole, and let's start with 1 liter. Okay, the pressure will be the same for the isotherm and the adiabat. This is your starting point. So the pressure was 22.4. So for the isotherm equation, from what we had up top, you can basically graph P equals 22.4 atmosphere liters times 1 over V, and you graph this, right? And then for the second graph at the higher temperature, right? See that one right there? I already showed you. This is what you'll graph. So you're basically graphing these two in Excel, these two lines. In the adiabatic world, the relationship for a ideal monoatomic, your adiabatic formula says this is true 5/3 or 1.67. So let's calculate P2. P2 equals this. See the parallel to over here. So the new constant I'm getting for the adiabat is going to be P1 times V to the 5 over 3. And I'm going to graph y equals this constant 1 over V to the 1.67, right? So when you do that one, you can calculate this, and you put your number one volume to that. But so this is your constant. So it's funny how the constant ends up being the same. The difference will be the 1 over V. It's not 1 over V by itself. It's 1 over V to the 1.67. So you're graphing this relation versus that isotherm. This is the second adiabat you're graphing versus that one. So long story short, what you're looking for is they talk about the Carnot cycle, right? What I need you to show me, this is just a rough printout here. So you can see how isotherm, and these two are the adiabats that are steeper, but I want you to blow up this region right here. So you take the time to put in more data points if you need it. So what you end up seeing is your first, well, your one adiabat, your second adiabat. See how it crosses the two isotherms. You shade in the area that gets blocked in from A, B, C to D. That's what we're looking for. This is exactly the Carnot cycle that's in your textbooks and everybody reads about, where you go from here to here isothermally. See how you're following the isotherm? And then from B to C, you switch to following the path on an adiabat. C to D goes back on an isotherm. And then D back to the start goes back on the adiabat to get back to where you started. That's the Carnot cycle. This is all done on a reversible sense too as well. So that is question 5. It's a graphing exercise for you to use Excel and make this happen.